the average of this. So let's say you call these some number xi's, where I is 1, 2, 3, that x1 is this, x2 is this, x3 is this, and so on. You want to find average x, average value of these numbers. So we can do it very simply. So there are two symbols used in physics to represent the average value. Sometimes people write it like this, x average. You write it whatever way, it works out like this: 1 plus 2 plus 1 plus 2 plus 1 plus 3 plus 4 plus 5 divided by 1, 2, 3, 4, 5, 6, 7, 8. Right? If you work it out, this is a number 3, 4, 5, 6, 7, 8, 9, 10, 14, 19 over 8. It's roughly 2.4 something. So that's how you compute the average number. But I want to derive another formula which we can use generally for a huge data set from this simple example. We can see that I can rewrite this thing like this. That say there are 1, 2, 3 ones. So it's essentially 3 into 1. Then there are 2 2s. Then there's only 1 3, 1 4, and 1 5. Okay? So we can write it like this. And now let me separate it into this part. 3 by 8 into 1 plus 2 by 8 into 2 plus 1 by 8 into 3 plus 1 by 8 into 4 plus 1 by 8 into 5. आप इसका भी करेंगे तो यही नंबर आएगा. But this now has a slightly different interpretation. ये 3 by 8 क्या है? This is the probability of finding 1 out of this sequence of numbers. Because 1 comes 3 times, the total of 8 numbers. So probability of 1's occurrence is 1 by 8, 3 by 8. This is the probability for this number 2 to occur in this sequence, which is 2 by 8, because 2 comes twice. 3, 4, and 5, they all come once, so their probability is 1 by 8. So you can do it like this, but symbolically I can write it like this. I goes from 1 to, there are 1, 2, 3, 4 numbers into PI xi. So PI, 1, 2, 3, 4, 5. So it goes from 1 to 5. So PI is the probability of finding ith number. x1 जो है वो 1 है और x1 की probability है 3 by 8 plus x2 जो है वो 2 है और उसकी probability p2 है 2 by 8. So अगर आपके पास large data set हो और उसमें कुछ numbers हैं वो बार बार repeat हो रहे हैं, तो instead of summing all of them up, you can do it like this: sum only the distinct numbers but multiply them with their probability of occurrence or their weight, and then you add it up. This gives us the average of that sequence. But this is for a discrete data set. For a continuous data set, the average of any distribution can be found like this. Okay, so this is P of x, probability of finding x into x, px. So this thing is the generalization of this rule when we have a continuous data set. So P of x is the probability of finding x, and this integral is just simply the sum over this product x into P of x. So this is the way we compute averages for continuous distributions, continuous data, and this is the way of computing averages for discrete data sets. Now, keeping this thing in mind, let's now come to the ideal gas. हमने ऑलरेडी इस आइडियल गैस में के लिए जो वेलोसिटी डिस्ट्रीब्यूशन है वो कंप्यूट की थी. दी velocity distribution, Maxwell velocity distribution, using Maxwell-Boltzmann distribution, and we found that the density of particle or number of particle per unit volume at a given velocity v is equal to, there was a constant a into an expression. Constant a मैंने कहा था कि आप नॉर्मल से फाइंड कर लें, and if you do that you get this expression. This m is the mass of this particle minus m v square 2 kbt. So this dV is just reminding us that this is per unit volume. This v, sorry, is for volume, not for velocity. Okay. So this is the number of particles per unit volume at a given velocity. So if we plot its graph, this number is something like this. It's rise higher and then it goes slowly like this. So particles have a most probable speed. Most probable speed कौन सी है? वो speed जो सबसे ज़्यादा जिसके होने का chance है. Then the particles have an average speed which is somewhat different from this, and then you can also compute the root mean square velocity of particles. Root mean square is that it's the average of the square of velocities, not the average of velocities. So if we want to compute the root mean square of this velocity distribution, I want to compute this thing. Root mean square velocity of particles. So ये क्या होगी? This is nothing but the square root of average of v square. कि पहले तो आप velocity का square find करें, which is simply v square, फिर उसकी average ले लें, and उसका square root जो है that is the root mean square velocity. So this, अब हमने v square की average find करनी है, तो उसका क्या तरीका होगा? v square की average होगी v square average is equal to v square into the probability of finding particle with velocity v square. So dV अगर आप ये रिप्रेजेंट करें वॉल्यूम को, so then यहाँ पे dV लगा लें, यहाँ पे dV लगा लें. So then this is the number of particles at a given velocity, because this n is the number of particles per unit volume. ठीक है? So अगर volume fraction से multiply करें, you get total volume. So you can also multiply with a small region of velocity. Actually, that is also physically meaningful, because if I do this, then this is the number of particle in a given velocity band. कि यहाँ से लेके यहाँ तक जो ये dV region है, इसके अंदर कितने particle हैं per unit volume. So we can actually use both. So this is the number of particles per unit volume per unit velocity. Okay? So if you multiply it with a small volume element, you get number of particles, total number of particles in that volume in a given velocity band. So if you multiply with a small velocity band, you get total number of particles per unit volume, because the velocity part is multiplied. But to remove confusion, we can actually just stick with this. That's even better. So this is the number of particles per unit volume per unit velocity. To get the average root mean square velocity, we need to find the average of v square, and to find average of v square, we simply multiply v square with its probability and integrate over the all velocities. So this v square average can then be written as, और इसी तरह से अगर आप फाइंड करना चाहें v bar average velocity, that would be V PV D. Okay? So this is the average velocity, that's the square of the root mean square, या simply average of the velocity square. जब अगर आपने जब VRMS फाइंड करना होगा तो इसका स्क्वायर रूट करेंगे. जो ज़्यादा useful है expression, that is the RMS value of the velocity, because that eliminates this part. क्योंकि जब molecules किसी container में हैं, they are going like there, here. So when you are finding average, this and this is being cancelled out. एक molecule जो किसी velocity से इधर को जा रहा है, दूसरा molecule इधर को जा रहा है, in that average that information is lost. So when you first take square, then essentially we get the velocity information in another sense. Essentially it's the speed information. Okay. So P of V square है probability of finding the square of velocity, and P of V is probability of finding velocity. But in our case actually they are both the same, because जो velocity की probability है वही V square की probability है, उसके जो corresponding V square है. Okay? So in the civilized world, when you ask a question, you look to the person when the person is answering the question. Okay? क्योंकि आप सवाल पूछ के वो इधर देखना शुरू करते हैं तो this doesn't say good things about you. या किसको आपको बुला रहा था? अब आप तो देखते इस तरह के केस में they will always be the same actually. When you have a sum variable x और उसके corresponding variable x square है, तो जो x की probability है जो corresponding x square है उसकी probability भी same है. So I'm just writing it symbolically to emphasize that you essentially need to find the average of a variable. You have the variable multiplied by its probability, okay? Or incidentally, for this situation and that situation, that probability is the same. अक्सर same होगी, yes, that's fine. Okay. Okay. So let's try to compute V bar. So V bar would be then definitely. So अब अगर जब मैं V bar find करूँ, चूँकि velocity is only a positive number, so it's going from 0 to infinity. We are talking about the magnitude of velocity. So we have V here, and probability of velocity is the number of particle per unit velocity divided by, इसको आप V से multiply कर लें, divide कर दें number of particle के, you get the probability of the velocity. अब ये जो n of V है, this is number of particles per unit volume, ठीक है? और अगर मैं इसको वॉल्यूम से मल्टीप्लाई कर दूं, हमारे पास टोटल नंबर ऑफ पार्टिकल की प्रोबेबिलिटी आ गई, और उसको आप टोटल नंबर ऑफ पार्टिकल से डिवाइड कर दें, सो देन दिस इज द प्रोबेबिलिटी ऑफ वेलोसिटी v फॉर वन पार्टिकल. सो दिस इज द एवरेज वेलोसिटी ऑफ अ पार्टिकल बाय डिवाइडिंग इट विद टोटल नंबर ऑफ पार्टिकल्स. सो इफ वी सब्स्टिट्यूट दिस n of v from here, we get v over n, some constant here, into vq minus mv square 2kbt d. So that constant जो भी इसके साथ वो लगा हुआ है, you put it there. अब चूंकि you we are not too expert in integration, so इसका just we can use an integral formula, और अगर वो formula use करें something like this, 0 to infinity z cube minus az square dz 1 over 2a square. इस तरह के जो integrals हैं जब एग्जाम में होंगे तो I'll give you the formula, okay? You don't have to worry about it. So ये इंटीग्रल इसके बराबर होता है where a here is this part. So all of this minus यहाँ पे, so this is a. तो ये a यहाँ पे रखें, ये इंटीग्रल वैल्यूड हो जाएगा, इसे मल्टीप्लाई करें, the answer that you get for v bar is 8 kbt over pi m. So this is the average velocity. इसी तरह अगर हम v स्क्वायर की एवरेज निकालना चाहें तो v स्क्वायर एवरेज जो है अब जो p of v है वो वही है जो इस केस में, so that p would still be n over n into v over n. उस p की जगह पे ये n v over n रखें, फिर इसी तरह का एक फार्मूला यूज करके तो जो v स्क्वायर है that comes out to be 3 kbt over m. So this is the v square average. ज्यादातर फिजिक्स में what we are interested in more is this v square average instead of this v average, and the reason is that kinetic energy of one particle is half m v square. जितने पार्टिकल हैं सबकी kinetic energy half m v square है, और सबकी velocity different है, सबका v स्क्वायर भी डिफरेंट है, सबकी काइनेटिक एनर्जी इन जनरल डिफरेंट है. लेकिन अगर हम एवरेज काइनेटिक एनर्जी फाइंड करना चाहते हैं, सो एवरेज काइनेटिक एनर्जी इसको यूं लिख लें या कुछ लोग इसको यूं लिखते हैं या कुछ ये सिंबल के. सो दिस एवरेज इज द एवरेज ऑफ ऑल ऑफ दिस. सो चूंकि ये कांस्टेंट है, ये कांस्टेंट है, अगर आप ये अज्यूम करें कि तमाम मॉलिक्यूल्स या एटम जो है सबका मास सेम है, सो देन दिस इज जस्ट अ कांस्टेंट. सो दिस एवरेज इज द average of v square. So here we need the average of v square, not the average of v. So that's why this number is more useful for us. So if I substitute this v square here, we get this 3 by 2 kbt. So average kinetic energy is 3 by 2 kbt in an ideal gas where particles are treated classically using Maxwell-Boltzmann distribution. So actually this was first proven by Maxwell, and this was a great success of Maxwell-Boltzmann distribution to explain a classical result which was also known from another theorem which is called the Equipartition Theorem. Equipartition Theorem says that it's called Equipartition Theorem, that each degree of freedom, let me first write it in the jargon, then I'll explain. Each degree of freedom has an average energy of half kbt. Okay, now if we have an ideal gas of point particles, and let's say it's free to move in three-dimensional space, the particle can either go along x-axis, or it can go along y-axis, or it can go along z-axis. Is there anything else that this point particle can do?
Move into 4 dimensions.
No, in 3 dimensions. In space, like in the 3-dimensional space, there are only 3 degrees of freedom. Equipartition theorem, and that is that each degree of freedom has an average energy of half kbt. So इसमें 3 degrees of freedom है, तो total energy कितनी होगी? Average total energy एक particle की कितनी होगी? 3 by 2 kbt. And in general, if you have f degrees of freedom, then the average energy of particle is half f kb. फर्ज करें कि ये जो पॉइंट पार्टिकल है, it's not in a gas but it's in a solid. So in the solid, so it's part of a lattice and it's bonded to other molecules and atoms in there. So this is, let's say, one atom, another atom, another atom, another atom. So each atom in a cubic lattice, in a three-dimensional lattice, is bonded to three other atoms. So not only that, when it moves in 3 dimensions, it has kinetic energy, but when, let's say, it moves in this direction, it also has a freedom to store energy in this spring, in this bond. So there are 6 degrees of freedom. So for a typical atom in a solid, there are 6 degrees of freedom. 3 degrees of freedom to store energies in the kinetic form and along the 3 direction, and 3 degrees of freedom to store energy in the 3 bonds that it is associated with along 3 dimensions. So here there are 6 degrees of freedom. So F is 6. Or let's come back to a gas, and instead of having point particle, instead of, let's say, having helium gas or argon gas, where atoms are pretty much alone and we can assume them to be point particle, let's say we have a hydrogen gas. The hydrogen gas can be modeled as 2 point masses connected with a spring. Now there are several degrees of freedom. The 3 is, जो 3 degrees है वो तो आप इसको फिर up to the 0th order approximation, or when this is not moving much, you can assume it to be a point, a total point, so it can move here, it can move here, it can move in this direction. So 3 degrees of freedom for linear motion, but this can also oscillate. So there's 1 degree of freedom for storing energy in this spring, but it can also rotate. And there are 2 distinct degrees of rotation. It can, let's say, rotate like this, or it can rotate like this. So there are total of, again, 6 maximum degrees of freedom. लेकिन होता ही है कि when you have a gas, not all degrees of freedom are actually unlocked. Not all are available. It depends on the temperature of the gas. For example, when the temperature is low, only the translational degree of freedom is active, because the energy, the kinetic energy, the average half kBt is low enough that it cannot excite these vibrational modes or rotational modes. When temperature increases, rotational mode have a smaller energy. You need low energy to rotate a molecule than to vibrate it usually. So if you keep on increasing the temperature, then these rotational degrees of freedom get unlocked. If you keep on increasing, then even the vibrational energies are unlocked, and you can they also play a role. So by definition, a point particle is that it's spherically symmetric. So but you if you have a point particle, there's no inertia, so you don't need any energy to move it. If you consider an extended particle like a sphere, then you need some energy even to rotate it like this. But here, when I'm saying point particle, we are saying that it has no dimension. G. So these are number of particles per unit volume. इसको मैंने वॉल्यूम से मल्टीप्लाई किया तो मेरे पास टोटल नंबर ऑफ पार्टिकल आ गए उनकी सो टोटल नंबर ऑफ पार्टिकल की प्रोबेबिलिटी टू बी इन वेलोसिटी v. For one particle to be at that velocity, I divide by the total number of particles. So this gives us the probability of finding a particle at velocity. Kb is a measure of translation from temperature to energy for the average energy. हम इसको यूज कर रहे हैं. Okay, so जी जी. Degree of freedom is a way of storing energy, you can say. Any way in which you can store energy is a degree of freedom. For example, if there's a motion along x-axis, you can store energy in the motion along x-axis. You can keep on increasing the speed, and more energy would be stored in the kinetic form. So along one axis, there is 1 degree of freedom. Okay, so similarly, if there is a spring between two particles, and the spring can vibrate, so you can store energy in a sense in the vibrational modes. So it means that we can predict the average energy of a particle using this equipartition theorem. And if you have, let's say, a mole of a system, a mole of a particle, a mole of a material, so there are Na particles by definition, so total energy in a mole of a particle would be Na into half kb f. And it's better to actually put a bar over it, because this is a kind of an average temperature that we are talking about of this material. So this is the average energy of a particle with f degrees of freedom. If it's a point particle and a gas, f is 3. If it's a point particle and in a solid, then f is equal to 6. And if it is, let's say, a diatomic particle, then f depends on temperature. At different temperature, f is different. But this is the average energy per particle. So if we have Na particle in a mole of a gas or a material, then the total energy in 1 mole is this. So based on this, let's define another very important quantity. It's called specific heat capacity. Well, जी आप शुरू में थी, आप किसी का मैसेज देते हैं क्योंकि इनको भी फोन आ रहे थे कंफर्म करने के लिए कि इज देयर नॉट. बहुत मिनट. Okay, so specific heat is the amount of energy that you inject or take out of a material so that its temperature changes by 1 Kelvin. So, and I'm only interested in this lecture in the heat capacity at constant volume. So I'm going to put a V at the subscript, and so this is you can say like this. So suppose you have a part of a material. It's either a gas in a container or a chunk of a material, and if you give it some energy, its temperature will change. Usually the temperature will increase. So if the temperature increases by 1 Kelvin, the amount of energy that you have given it is called its specific heat or heat capacity. And if during this process the volume remains constant, it's called heat capacity at constant volume. There is another specific heat which is at constant pressure. We are not going to discuss it. So even if I put a V here or not, it's the constant volume specific heat that I'm talking about. And if this material is such that only 1 mole of material is here, then this is a molar heat capacity. Okay, but we are not going into this jargon that it's molar or not. From heat capacity, a specific heat, we actually mean the amount of heat that we add to change the temperature by 1 degree Kelvin. So this is du by dt. And if you talk about 1 mole of a material, then it is molar heat capacity. If you talk about any other material, then it's the heat capacity of that material. So let's say we have 1 mole of an ideal gas, and that ideal gas is helium. So for helium, and we have 1 mole, so that there are Avogadro's number of particles in air, and since helium is very good approximation of a point molecule. So all molecules in this container can be modeled as point particle. So at a temperature which is higher than its boiling point, the degrees of freedom would be 3. ये तकरीबन 4 डिग्री केल्विन पे जाके लिक्विफाई होती है. अगर आप उससे ऊपर वाले टेम्परेचर में है, then F is equal to 3 because these are point particles. So इसके लिए अगर हम स्पेसिफिक हीट इसके निकालना चाहें तो क्या होगी? So इसकी जो U है, it is Na 3/2 kB. So the heat capacity is du by dt. So क्योंकि F3 है, so this is 3/2 Na kB because ये T का 1 हो जाएगा. This number Na into kB has another name as well. It's up to you want to use it or not. अब ये भी रख लें, वैल्यूज यहीं पुट कर लें. इसका ये फायदा है, दिस इज यूनिवर्सल गैस कांस्टेंट. दिस हैज this value 8.31 joules per mole per Kelvin. So इसका मतलब है कि हीलियम, आर्गन, जितनी भी ये सारी पॉइंट पार्टिकल्स वाली गैसेस हैं, इन सब की जो हीट कैपेसिटी है, इट्स एक्चुअली फिक्स्ड एंड इंडिपेंडेंट ऑफ द गैस as long as temperature is higher than the boiling point. So if I plot it as a function of temperature, the heat capacity is fixed as 3/2 R.
So T bar was actually same.
This is the change in temperature. Okay, so this can roughly be written as du by dt as well. So this is the change of u with respect to t. T bar को 1 कैसे? क्योंकि इसका जब डेरिवेटिव लेंगे with respect to t, so this average, wherever we are dealing with temperature, it's average temperature. Okay, so if I put bar or not, so when we take the derivative of the average temperature with respect to average temperature, we get 1. So this is the heat capacity of helium. अगर आपके पास हाइड्रोजन है, okay, हाइड्रोजन गैस, so for hydrogen gas, अगर इसकी हम हीट कैपेसिटी देखें तो above a certain temperature when it is in gaseous form, इसकी भी हीट कैपेसिटी तकरीबन इतनी ही होती है. लेकिन after a certain temperature the heat capacity increases and it becomes, and this is where the rotational modes get unlocked. ये जो rotational degrees of freedom है, 2 वो आ जाती हैं, तो कितने हो जाएगा? ये 5/2 R हो जाएगा. Okay? So ये हाइड्रोजन की हीट कैपेसिटी है. शुरू में इसकी भी जो हीट कैपेसिटी है वो 3/2 R है क्योंकि F3 है. But later on when temperature sufficiently increases, that there is enough energy to make it rotate. So 2 degrees of freedom of rotation are also get active. So F कितना हो जाएगा उसके लिए? 5 हो जाएगा. तो हीट कैपेसिटी हाइड्रोजन की हो जाएगी 5/2 R. और इसी तरह अगर टेम्परेचर और बढ़ जाए तो जब इसकी जो वाइब्रेशनल मोड्स हैं वो भी अनलॉक हो गए हैं, then its energy is 3 R because F is number of degrees of freedom. Okay, so अगर हमारे पास सॉलिड है, ठीक है, एक टिपिकल सॉलिड है, उसकी हीट कैपेसिटी कितनी होगी? 3 R क्योंकि उसका F है 6. So F6 means that यहाँ पे 6 होगा, तो आप उसकी कैपेसिटी निकालेंगे तो आपको मिलेगी 3 R. So for solids we should expect the heat capacity to be, let's say 3 R. लेकिन जो ज़्यादातर सॉलिड्स हैं उनकी जो हीट कैपेसिटी है एक्चुअली फॉलोज दिस ट्रेंड. फॉर एग्जांपल लेड very quickly approaches this value. Then iron, aluminum, gold, they ultimately approach this value, but there is this slight curve. And this behavior actually cannot be explained by the kinetic theory of gases and this equipartition theorem. You have exhausted your quota. कितने लोग इसे एग्री करते हैं कि इसने एक सवाल नहीं पूछा? Okay, so this is, so you're allowed 2 questions. Let's ask the first one. इसीलिए आपको सवाल करने की जो ना वो कुछ लोग मुझे बाद में कहते हैं कि बार-बार हिग्स का नाम आ जाता है, हमें पता नहीं चलता किधर चले। We are dealing with classical particle, with a point particle, have nothing to do with their internal structure and everything. For all of these laws, so all of this discussion is for point particles, have no internal structure, simple point particle. Okay, it's classical description, Maxwell-Boltzmann statistics. क्योंकि सॉलिड का F3 है, F6 है, okay? Because there are 3 degrees of freedom for kinetic energy and 3 degrees of freedom for potential energy, because they are associated with bonds on 3 sides. So there are a total of 6 degrees of freedom. So when F is 6, 6 by 2 is 3. So Na 3 kBt. So we should expect the heat capacity to be 3R. गैसेस के केस में 3R होगा हायर टेम्परेचर पे, और वो भी सिर्फ हाइड्रोजन गैस के लिए, नॉट ऑल गैसेस। अगर आपके पास हीलियम गैस है, you should always expect it to have a heat capacity of 3 by 2R. Okay, हीलियम के लिए तो कभी भी नहीं होगी। हाइड्रोजन के लिए, because there are only 3 degrees of freedom, the helium atom can go here, here or up. But hydrogen atom, क्योंकि वो diatomic molecule है, it can rotate. So there is 1 degree of freedom like this, and it can rotate on its axis. So there are 2 degrees of freedom for rotation. And since it's a diatomic molecule, you can imagine like 2 masses combined with a spring, so it can vibrate like this. So that's the third. So at higher temperature, all 6 degrees of freedom are available. So ultimately, the hydrogen gas heat capacity also approaches 3R. But at a lower temperature, when energy is not high enough to vibrate it or to rotate it, there are only, really speaking, 3 degrees of freedom available. So that's why at low temperature, hydrogen's heat capacity is also 3 by 2R. Okay, so we have now been discussing heat capacities of these materials, these classical gases or classical solids where atoms are point particles, and we assume that they are not interacting with each other. Okay, there is no force that is interacting with that is acting on them. So we have a lot of particles. For example, gas molecules. We imagine that when one is here, the other is here. They are moving around. There is no force. The force only comes into play when they go towards each other. They strike each other, and then maybe after strike they go like this. And that's the only point when they come into contact. And that contact force, we model it as the random motion of particles, not as a force per se. But there is, and all of these systems have this very important property that when you add energy to them, their temperature increases. So their heat capacities are positive. To increase the temperature by 1 Kelvin, you have to add energy. So the heat capacity, which is del U by del P, when this increases, so this ratio is positive. But there is one system of particles which has a negative heat capacity, and that is sorry, solid T, because solid is a system in which atoms are connected with each other through bonds. So there are 3 degrees of freedom for 3 direction of motion of atom, and then there are 3 degrees of freedom with each atom for storing potential energy in these springs. Okay, so 3 for storing potential energy along 3 axes, and 3 for storing kinetic energy due to motion of these atoms. So that's why F is equal to 6 for solid. Okay, so there is one system of particles, and that is system of, let's say, masses, which if we imagine them to be interacting via gravitational attraction. So this system of particles, and you can imagine as many as you want, you can imagine them to be, let's say, a dust cloud. So the trick is working. Okay, so we have this system of dust particles which is attracting each other via gravitational attraction. This is a system which has negative heat capacity, and this is the only system out of these particles that we are studying which has a negative heat capacity, and it plays a very important role in the formation of stars, which is going to be the topic of our next class. I'm going to continue on this, okay? So this is a system कि अगर आप इसमें एनर्जी ऐड करें तो इसका टेम्परेचर असल में कम होता है, एंड इट्स अ सिस्टम कि अगर आप इसमें से एनर्जी निकालें तो इसका टेम्परेचर जो है वो इंक्रीज होता है. बट बिफोर अंडरस्टैंडिंग दिस कॉन्सेप्ट यू शुड उसको चीटिंग कराने के लिए जा रहे हैं और उसको बुला रहा क्विज होगा तो मेरे पास ही बैठे घर से आ रहे हैं मुझे 2:30 बजे जुम्मा पढ़ के निकल रहा तो 2:35 तक पहुंचता है. Okay, so before understanding this thing, that this dust cloud, when you add heat into it, its temperature decreases, and when you take out heat, its temperature increases. You have to understand what we mean by temperature. Temperature is nothing but a measure of the velocity of a body. Okay, so the particles that form the gas or the system, if they are moving more rapidly, their temperature is higher because their kinetic energy is higher, and if they are moving slowly, their temperature is lower. So the dust cloud is a system of particles that if we add energy into them, their velocities decrease, and when we take out energy, their velocities decrease. To understand this, let's begin with the two particle system. So let's say we have two masses. One is a big mass and the another one is, आप लोगों को कोई शर्म नहीं है? We imagine that this one is stationary and the other one is going around it. This is the general motion that is possible for two particles. It's almost like a hydrogen atom, but the hydrogen atom is made up of two masses which are attracting each other through this gravitational force. So this is the force of attraction between them, and we know that this system will remain revolving, this particle will remain revolving around it if the force of gravity provides the centripetal force to this mass to remain directed towards this particle. So we have a now system in which we assume that this is stationary, which we can do, let's say, by putting our reference system on this point, and then the only one particle is moving, which is this small particle with velocity v. So in this case, the temperature of this two particle system essentially only depends on the velocity of this particle. So the force of gravitational attraction is providing the centripetal force, which means that we can compute this velocity v squared by equating them. So m v square over r is equal to g m over r square. So v square is equal to, एक r cancel हो गया, एक m भी हो गया, this is g m over r. So this is the v square, velocity square. So what's the kinetic energy of this particle? So kinetic energy is half mv square, which is of g m over r. And what's the potential energy of this system? The potential energy is minus g m over r. So now this is the potential energy minus gmm over r, and this is the kinetic energy half gmm over r, which means that if I write total energy is the sum of these two, which is minus 1 plus half so minus half gm m over r, which we can now use to state these few relations. So total energy is equal to minus half gmm r, और ये क्या है? This is negative of the kinetic energy, minus kinetic energy, और या इसको लिख लें आप is equal to plus potential energy, because sorry ये minus half of potential energy. Potential energy is defined for a system always in such a way कि आप इसका negative derivative लें, you get the force. So minus d by dr of this gives us the gravitational force. Now, so this is the most important relation to understand what I was saying earlier. अगर फर्ज करें यही सिस्टम है, इसकी जो टोटल एनर्जी है वो देखें इट्स इक्वल टू माइनस काइनेटिक एनर्जी. अब अगर सिस्टम की टोटल एनर्जी कम होगी तो काइनेटिक एनर्जी इंक्रीज होगी या डिक्रीज? अगर टोटल एनर्जी कम होती है तो जो इसकी काइनेटिक एनर्जी है वो इंक्रीज होगी या डिक्रीज? नहीं, मैं काइनेटिक एनर्जी की बात कर रहा हूं. टोटल काइनेटिक एनर्जी जो भी है कि जब ये जो है ये कम होती है तो जो ये क्वांटिटी है काइनेटिक एनर्जी की ये बढ़ेगी या कम होगी? It should increase, right? Because for this to decrease, this number has to increase. क्योंकि ये माइनस है ना, तो अगर इस नंबर ने कम होना है तो ये जो पार्ट है इसे बढ़ना चाहिए, और ये बढ़ेगा तो काइनेटिक एनर्जी बढ़ेगी. So it means if we have this two particle system, for the two particle system we can say this thing that if the total energy of a system decreases for this gravitational system, its kinetic energy increases. लेकिन ये मैंने यहाँ पे जो आपको roughly show किया है, it's only true for these two particle system. Actually, this can be generalized, which we are not going to do, for lot of particles. If you have them which are here with, let's say, I12, can go to any n, and if you compute their, and all of them are interacting gravitationally, if you compute their average kinetic energy, this is equal to, यहाँ वही रिलेशन बनेगा जो यहाँ से बनेगा, which is minus half of average potential energy, and the total energy average is equal to the negative of the kinetic energy. So अगर आपके पास इस तरह का कोई let's say dust cloud है, we already know from the last lecture that every dust cloud must decrease its energy because of black body radiation. Everything. I'm standing here, these boards, everything that you're looking at yourself, even if you're completely stationary, you're radiating black body radiations. So that emission of radiations is decreasing your total energy. So this dust cloud, which is actually a very established, evident theoretically and by the observations, way of forming stars, that it begins from a dust cloud, and simply because this dust cloud is interacting gravitationally, it's radiating slowly. अब देखिए शुरू में जब dust cloud होता है उसका temperature होगा maybe 0.1 Kelvin, 10 power minus 1 Kelvin, almost near absolute zero. But still at that temperature it's radiating, but very faint radiation. So over the course of billions of years, it keeps on radiating, but as it radiates, it loses its total energy. So these particles which are just slowly moving around, they begin to move around faster. And the dust cloud is also collapsing, so it's getting smaller, but the particles are now moving more violently. And as they move more violently, their temperature increases. So because of increasing temperature, the radiation increases. So the process accelerates. जितनी ज़्यादा radiation निकलती है, उतने ज़्यादा particles का temperature बढ़ता है. So this system gets hotter. So as it gets hotter, मैंने कहा कि this can be generalized to many particles. That remains true. I'm not going to prove it, but the same conclusion holds true for many particles. And actually, you can make sense of it as well. अगर तो मैं ये prove करता ना एक proton electron के लिए, then I wouldn't be able to generalize to say, okay, if you inject more electron and protons, the system will scale up. क्योंकि electron जब आप एक ऐड करेंगे प्रोटॉन इलेक्ट्रॉन सिस्टम में, तो वो इलेक्ट्रॉन कुछ के साथ वो रिपेल कर रहा है, कुछ के साथ वो अट्रैक्ट कर रहा है. So you cannot generalize the result of two electron, one proton, one electron, two electron proton. लेकिन if you have all dust particles, all are neutral, and they all are just attracting, it's very easy to generalize. If you add another one, it's going to attract all those three, and then the same conclusions hold. But each one is attracting each other through the same gravitational attraction formula. Okay, so this process, when this radiates more, then this becomes hotter. So as the cloud collapses, it gets hotter and it gets smaller. और उसकी वजह से जब ये hot होता है तो और ज़्यादा radiation निकलती है. So the process becomes faster, and शुरू में process slow when a star is forming, but eventually the process gets faster and faster. And actually, it's the same process of forming even planets. क्योंकि जब star बनता है ना, you have a big gas cloud. It begins to collapse, and उसके center में तो star बन गया, लेकिन जो थोड़ा left out material है, it is revolving around the star, and that left out material follows the same logic. The different chunks, they keep on collapsing each other, make bigger dust particles, then they make bigger stones, then those stones get together. इसलिए जितने भी planets हैं initially when they are formed, at the center they are hot. Even हमारी Earth जो है, it's very hot at the center. It's still part of that process. Then that collapsing thing increased the temperature of this planet a lot. अब बाहर से तो काफी cool down हो चुकी है, but still the cooling effect is continuing and the Earth is radiating. So maybe over the next a billion years, it will cool down such that even the core would be dead. Because we have reached that point where the matter, you can say, is to the point that it's being supported by the degeneracy pressure of the atoms. You cannot squeeze it further. The gravitational force is not strong enough. If you have more mass, more than a critical point, then it keeps on decreasing. When the degeneracy pressure of fermions cannot support the gravitational collapse factor. Temperature अगर आप यहाँ से देखें, ये बात आप समझ गए कि टोटल एनर्जी जब कम होगी तो काइनेटिक एनर्जी बढ़ेगी। तो काइनेटिक एनर्जी बढ़ने का मतलब क्या है, जो वेलोसिटी है वो बढ़ रही है पार्टिकल्स की। सो टेम्परेचर इज नथिंग बट द मेजर ऑफ एन एवरेज ट्रांसलेशनल वेलोसिटी ऑफ अ सिस्टम ऑफ पार्टिकल। हाँ, क्योंकि बिल्कुल उस वजह से टेम्परेचर। सो दिस इज अ सिस्टम ऑफ पार्टिकल विच इज कंपोनेंट टू इट, because its temperature increases as it radiates. But they're collapsing on each other. Okay, so for example यहाँ पे dust particle यहाँ पे है, तो वो बेशक velocity तो बढ़ रही है, लेकिन gravitational attraction तो सब पे है। दो dust particle है, they have come closer, so they have become they are coming closer. Similarly, जैसे वो system है, the mass is coming towards the smaller mass is coming towards the bigger mass because of the gravitational attraction. So the attraction is pulling all of these things together.
So radiation simultaneously हो रही है, radiation का कोई किरदार है इसको?
Simultaneously हो रही है, as the cloud is radiating, it's collapsing, and it's getting hotter. All of these things are happening.
तो ये क्या radiation से इफेक्ट होता है कि ये कॉम्पैक्ट होता है, या तो radiation एक अलग चीज है और उसका जो है ना gravitational pull के अंदर छोटा होता है एक अलग चीज?
Everything is happening simultaneously. The gravitational pull is there. The gravitational attraction makes the system such that when it radiates, its kinetic energy increases, which increases temperature. Heat is not temperature. The energy is there, but energy is not temperature. So this is our common experience from everyday things that we do in our life. So the point of this last part is that that's not universally true. Okay? So this is one reason why, for example, the fusion has to be ignited in a star to make it stable. Because if there's no source of energy inside a star, it will keep on collapsing. So that addition of energy by the fusion reaction inside the core of a star, that actually helps make it stable to stop its further collapse. Because addition of energy reduces temperature. Reduction makes the velocity smaller. Okay, so actually people have done a lot of simulations for these processes, and not only simulations. Recently, the pictures taken by different galaxies and star-forming regions have confirmed these theories. And the point of calling all of you here, okay, was this, that from this point on, we are now changing gears, and the last 2 weeks we'll spend on studying mathematically the physics of stars. So even if you are feeling left behind, you should try to join us. Okay, so we'll take quiz, okay, but at the end. It's not the end, right? So I'm going to show you first the simulation of a star-forming region, and then we will see how the actual observations have confirmed this thing. And while you look at it, don't forget to look at the time scale over there. And this is just a computer simulation. confirm these theoretical predictions that we do in computers.
A spectacular new NASA ESA Hubble Space Telescope image, one of the largest ever released of a star-forming region, highlights N11, part of a complex network of gas clouds and star clusters within our neighboring galaxy, the Large Magellanic Cloud. This region of energetic star formation is one of the most active in the nearby universe.
This is the Hubblecast, news and images from the NASA ESA Hubble Space Telescope.
The Large Magellanic Cloud, or LMC, contains many bright bubbles of glowing gas. One of the largest and most spectacular has the name LHA-120N11, from its listing in a catalogue compiled by the American astronomer and astronaut Carl Henneis in 1956, and is informally known as N11. Close up, the billowing pink clouds of glowing gas make N11 resemble a puffy swirl of fairground candy floss. From further away, its distinctive overall shape led some observers to nickname it the Bean Nebula. The dramatic and colourful features visible in the nebula are the telltale signs of star formation. N11 is a well-studied region that extends over 1,000 light-years. It is the second largest star-forming region within the LMC and has produced some of the most massive stars known. It is the process of star formation that gives N11 its distinctive look. 3 successive generations of stars, each of which formed further away from the centre of the nebula than the last, have created shells of gas and dust. These shells were blown away from the newborn stars in the turmoil of their energetic birth and early life, creating the ring shape so prominent in this image. Beans are not the only terrestrial shapes to be found in the spectacular high-resolution image from the NASA ESA Hubble Space Telescope. In the upper left is the red bloom of the Rose Nebula N11A. Its petals of gas and dust are illuminated from within, thanks to the radiation from the massive hot stars at its center. The Rose Nebula is relatively compact and dense and is the site of the most recent burst of star development in the region. Other star clusters abound in N11, including NGC 1761 at the bottom of the image, which is a group of massive hot young stars busily pouring intense ultraviolet radiation out into space. Although it is much smaller than our own galaxy, the LMC is a very vigorous region of star formation. Studying these stellar nurseries helps astronomers understand a lot more about how stars are born and their ultimate development and lifespan. Both the LMC and its small companion, the Small Magellanic Cloud, are easily seen with the unaided eye and have always been familiar to people living in the southern hemisphere. The credit for bringing these galaxies to the attention of Europeans is usually given to Portuguese explorer Fernando de Magellan and his crew who viewed it on their 1519 sea voyage. However, the Persian astronomer Abdul Rahman al-Sufi and the Italian explorer Amerigo Vespucci recorded the bright galaxy in 964 and 1503 respectively.
Okay, so now the quiz.
So how were they able to visualize it?
With the telescope? So they were talking about their success. They were not talking about the distance of that cloud from Earth. They were talking about the extent of the cloud itself. Okay? Or, अगर फर्ज करें, let's suppose distance ना होगी, तो light is still coming. इसका उससे भी जो ज़्यादा दूर वाले stars हैं and galaxies we have been able to see. Okay? Even आप मेरे ख्याल में आप जो distance हम देख सके हैं, they are about 10 billion light years away. So 30.8 billion light years. It's faster. So the next 4 lectures will be on the stars and how they form and how they evolve. And most likely in all of those classes, we will have either we'll have one quiz. So its weight will also could be higher and would be inversely proportional to the number of people present in the room. So